In this video, we're going to graph an equation written in vertex form and then identify its key components. So when looking at a quadratic, there are two key components that every quadratic or parabola graph is going to have. One of them is called the vertex point, and that is the point on the graph where the parabola changes direction. So if you notice carefully, there's a part of the graph where the parabola is going up and a part of the graph where the parabola is going down. And what happens is there is a point of change where this direction actually changes, and that is called our vertex point. So in the parabola that you see on the screen, our vertex point is going to be the point x is 2, y is 1, because we can see at that point we change from the graph going up to the graph going down. Then the second thing that every single parabola or quadratic function is going to have is it's going to have what's called an axis of symmetry. And it's a line drawn on the graph that basically divides the parabola in half perfectly and is a line of symmetry. It means it's the same on both sides. And if you look carefully, here is our line right here. If we flip or fold on that green line, the parabola will actually fold onto itself. And this is a vertical line that occurs, notice, when x is equal to 2. So our axis of symmetry equation line is x is equal to 2. So on every single parabola or quadratic function that we see, we're going to have an axis of symmetry, as well as a vertex point where the graph changes direction. So let's practice identifying these key values for the equations that you see up above. So you can see here we have three different equations, we have three different graphs, and each has a different vertex and axis of symmetry. So let's take the time to identify them. In this first example, I see that my vertex occurs at x is -2, y is -3. Here I see that my vertex occurs at x is 4, y is 2. And here I see that my vertex occurs at x is -3, y is -1. Then from here, I also need to determine my axis of symmetry. And if I look carefully here, I notice that there's a vertical line I can draw here at x is -2. So my axis of symmetry is x equals -2. Here, my axis of symmetry is right here at 4. So I have x is equal to 4. And then here I notice, if I look right here, I have where x is equal to -3. So pretty easy to identify when we have the graph in front of us. What I hope you're also noticing is there are some really interesting patterns here that actually allow us to find this information very quickly, especially if we have an equation in front of us. So first thing I hope you're noticing is that the x values of your vertex match your axis of symmetry. So the x value of your vertex matches your axis of symmetry. This occurs because the vertex is the point that's right in the middle of the graph where we can fold it, and it will be the same on both sides because it's the point where the graph changes the direction that it is going. So that's the first pattern that I hope you are seeing. The second pattern I hope you are seeing is that this vertex point actually relates up to your equation. So take a moment and look at your vertex and your equation. Your vertex and your equation. And if you look carefully, what you're going to notice is that your vertex is actually hidden inside of this vertex form equation. So we know from vertex form that our h value inside of here is going to move the graph. It's the opposite of what we expect. So left 2, down 3. That's why our graph moved the way that it did. Well, if you look carefully, it's the opposite of our h value and our k value that make up our vertex. -2, -3. +4, +2. -3, -1. So it's our opposite of what's inside of the parentheses here with x, and then the k value on the outside. So we can actually look at a vertex form equation and identify our vertex, hence why it is called vertex form. So while we are going to graph our own functions soon, we're going to start by being able to identify a lot of the key information that we see on a graph. So on this particular graph, you can see the graph of y equals -3x times the quantity of x plus 2 squared plus 3. So we need to identify all of this key information that we see here. So the first thing I see is my vertex. I know that's the point where I change direction. So here I see that I have the point x is -2, y is 3, which matches what I expect in my equation, opposite of what's being added in there with x, and then the k value on the outside. Then our next thing is our axis of symmetry, which is the line that divides our graph in half. It's the line where if we folded, it would match up perfectly. And remember that our axis of symmetry and our vertex share that x value. So we have x is equal to -2. Then from here, we need to identify our y-intercept point. And if you forgot this from Algebra 1, remember our y-intercept is where we cross the y-axis. And our y-axis is right here. Now what's a little tricky is we can't quite see, but where this is going is it's about to hit the y-axis at y is -9. So if you were to expand that a little bit, you'd be able to see that we cross the y-axis when we hit at y equals -9, so our y-intercept point is 0, -9. Then from here, we're looking for the x-intercept points, which are where we cross the x-axis. So if you forgot that, make sure you make a note of that. And there may be a time where we have multiple x-intercepts, which is the case here. We cross the x-axis twice. So here we cross the x-axis at -3, 0, and at the point -1, 0. Now the next thing we're going to do here is we're going to determine if the vertex is a maximum or a minimum point. So this is where we're going to look at the shape of the graph itself and determine, is it a minimum or is it a maximum? So what I want you to notice here is that our graph is going up, 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 and it hits this high point here, and then it's going down. So when we say is our vertex a maximum or a minimum point, we're saying looking at the graph as is that vertex the highest point on the graph, which would make it a maximum, or is it the lowest point on the graph, which would make it a minimum? And here I notice that my point is my highest point on the graph. That's what it is, which makes this vertex point a maximum point. Then lastly, I need to determine my domain and range, and I notice that my graph is going forever to the left and forever to the right, so my domain is all real numbers. And then my range, my y values that I need to make points on my graph, start at 3, and then they go down. So my range is going to be y is less than or equal to 3. So in addition to the key components that we just found on the previous slide, we're also going to find increasing and decreasing ranges. So an increasing range is where the graph is going up. So we can see here, it's different depending on the shape of the graph. And our decreasing range is where the graph is going down. So here we're going down, and here we're going down. So we're going to write an inequality to represent the ranges where we are decreasing and where we are increasing. So if we go back and take a look at the graph we were identifying key features on before, we're going to identify the increasing and decreasing ranges for this particular graph. So here's my vertex point, and what I notice is that I am increasing, or I am going up, everywhere on this side of the graph. So this is where my increasing range is. Now what I notice is that it starts at -2, and then it's going to the left of -2. So all of these values that are more negative or smaller than -2. So my increasing range, you can write this in a couple of ways, but if you just want to write to the left of -2, that is fine. You could also write where x is smaller than -2. That's the quicker way to reference that, because we're going to the left, or we're going smaller than -2. Then our decreasing range is going to be over here. This is where our graph is going down. And so again, you take a note and you say, well, this is to the right of -2, or you can just simply say x is greater than -2. That is where we are decreasing, that is where the graph is going down. Now, the reason we're not including an equal to in those inequalities is because at this point, x equals -2, it's not increasing or decreasing, it's just still. So just kind of keep that in mind. It's not going up, it's going down. It is changing direction at that point. So that's why there's no equal to in those particular inequalities. So this says graph the equation in vertex form below and then identify the key information below. So we're going to start by looking at the fact that this is in vertex form. So I can find my vertex very quickly by taking the opposite of 2, because that's going to move us 2 to the right, and we go down 8 units. So we have a vertex of 2, -8. I then have an axis of symmetry that matches that of x is equal to 2. So we can go ahead and we can label those right on our graph. So we have, here is our axis of symmetry, that's where our graph splits in 2, and we know that our vertex is down here at 2, -8. So we can label those right off the bat. Now, we know that our vertex is in the middle of our graph, so I'm going to put that in the middle of my table here, and I have a vertex of 2, -8. Now, from here, there are a couple of different ways that you can calculate your table. What I suggest you do is pick a couple of points around this. We're going to go to 3 and to 4, to 1 and to 0. Now, if you want to calculate these by hand, this is pretty easy to do. So if I show you an example, say we're doing 0, you would do, okay, when x is equal to 0, so you have y is equal to 2, you have 0 minus 2 quantity squared minus 8. Well, if we follow the order of operations here, 0 minus 2 is -2, so that inside becomes -2. -2 squared is 4, so you really have 2 times 4 minus 8. So this becomes 8 minus 8, which is 0. So calculating these by hand is pretty easy to do if you know your order of operations. The other option you have is to type this entire thing into your calculator and replace x with whatever x is currently equal to. So you could, in your calculator, if you wanted to calculate x is equal to 1, just type in 2 parentheses 1 minus 2 quantity squared minus 8. You should be able to calculate all of these by hand, but if you choose not to, that is okay. And what you should see happen here is this one becomes -1 squared, so that's 2 times -1 squared is 1. So that becomes 2 times 1 is 2 minus 8 is -6. Now, if you plug the rest of these into your calculator or you calculate them by hand, what you will notice is there is symmetry around that vertex point. So you'll notice here that we go up to -6, then we go up to 0. So here if we go to our graph and we plot those points, we're at 1, -6, 3, -6, then we're at 0, 0, and 4, 0. So here we can draw a sketch of our quadratic and we can see a parabola on our graph. So the next thing we need to do here is identify the rest of our key components. So our y-intercept is where we cross the y-axis, which in this case is the point 0, 0. Then our x-intercepts are where we cross the x-axis, which occurs twice at 4, 0 and 0, 0. So 0, 0 is kind of a special point. It's both the x-intercept and the y-intercept. Then from here, our domain, because we're going forever to the left and forever to the right, is all real numbers. And our range starts at -8 and goes up. So we have y is greater than or equal to -8. Then from here, we need to identify our increasing and decreasing parts of our graph. Well, we are increasing, and I'm going to try to make this as clear as I can, we are increasing over here to the right of x is equal to 2. Or, remember, you can write this as x is greater than 2. That's the quicker way to do it because you can just give a range using an inequality. Now the decreasing range over here, this is where we are going down, this is where we are decreasing. That is to the left of x equals 2, which again you could then write as x is less than 2. That's the quicker way to do it, just using an inequality. Then this last piece here asks us to identify if the vertex is a minimum or a maximum point. And if I look down here, this is the lowest point on the graph. And because it's the lowest point on the graph, that vertex is a minimum point. All right, so second example here. So again, we can see that we have an equation that is written in vertex form. So what we can start off doing with this equation is we can immediately find our vertex. Remember, our vertex is the opposite of what is in here with x, so it's -5, so it's going to move to the left 5, and then up 1. So our vertex point here is -5, 1, so we can go immediately to that point right there. And then our axis of symmetry and our vertex share an x value, so our axis of symmetry is x is equal to -5. So I can immediately draw that in there and see where my graph is going to be cut in half. Now remember, our vertex is the middle of our graph, so it goes in the middle of our table. And then I want to pick some x values around that. So I'm going to pick -4, -3, -6, and -7. So remember, from here you have a couple of options. You can either plug them into your calculator or calculate them by hand, and you should expect to see some symmetry. So I'm just going to calculate some by hand quick here because I can do that pretty quick. So x is equal to -7. Well, I know that this is a -1 out in front here, so I have y is equal to a -1 times, that's -7 plus 5 squared plus 1. Well, I know that this inside piece here is going to become -2. -2 squared is 4. So this is really -1 times 4 plus 1. So that's -4 plus 1, which is -3. And then I expect to see symmetry, so on the other side it would also be a -3. Then from here I can do x is equal to -6. So I have y is equal to -1 times -6 plus 5 all squared plus 1. Again, using order of operations, -6 plus 5 is -1. -1 squared is just 1. So I have -1 times 1 plus 1, which turns into -1 plus 1, which is 0. So here I have 0, and symmetry on the other side also makes that 0. So here if I plot my points, I have -6, 0, -4, 0, and then I have -3, -3, and -7, -3. So I can see a nice sketch of my graph here. Now, this next one with the y-intercept is a little bit tricky because we can't actually see where we're crossing the y-axis over here. But what we do know about our y-intercept is that our y-intercept lies on that y-axis. And what we know about that y-axis point is that every single x value on this particular y-axis has an x value of 0. So if we need to, we can actually calculate our y-intercept by hand. And all we need to know is that this occurs when x is equal to 0. That's how we lie on that line. So if we calculate that, which I can do right over here, we're just going to calculate what happens when x is equal to 0. So here we have y is equal to -1. So we have 0 plus 5 all squared plus 1. Well, this inside piece here becomes 5, and 5 squared is 25. So we have y equals -1 times 25 plus 1. So that's -25 plus 1, which is -24. So that tells us why we're not seeing it on our graph. That's because our y-intercept is occurring when x is 0 and y is a -24. Then our x-intercepts occur when we cross the x-axis here. So that's occurring at -6, 0 and 4, 0. Then from here, our domain, we're noticing the graph goes forever to the left and forever to the right. So that's simply all real numbers. And then our range, we start here at y is equal to 1 and we go down. So our range is y is less than or equal to 1. And then if we look at our increasing and decreasing parts of our graph, we are increasing here. Our graph is going up when we are left of x equals -3. Now, if you don't want to write that whole statement there, left of x equals -3 is when x is less than -3. It's on this side of -3. Then our decreasing range is over here to the right of -3, and that's where x is greater than -3. And then the last thing we need to identify here, our point right here, our vertex, is the highest point on the graph, and as a result, this vertex is a maximum point.